The final section of vector value functions, we're going to study two last topics, arc length and curvature. The arc length is actually a revisit of something that you did in Calculus 2. And you might recall in Calculus 2, if you had a parameterized function, what you would do is you would take the derivative of each of the coefficients of I and j, and from there what you would do is you would just stick them under a radical and then integrate the squares of those derivatives. Alright, and that's essentially what we're going to do here, except it's going to be in 3 dimensions. Alright, so let's say for some reason that we have a smooth curve defined as r of t is f at ti, g of tj, h at tk, and we have an interval ab. The length of that arc of the vector value function, we're going to define that as s, is going to be equal to integral from a to b, f prime squared, g prime squared, h prime squared under the square root. Or, in other words, it's just the magnitude of the derivative with respect to t. Alright, so let's go ahead and see if we can evaluate the arc lengths for several different functions. Right? So the first one we have is a pretty easy one, okay, just all linear stuff, just to illustrate how to go through this. So we have r of t is negative ti, 4tj, 3tk. Alright, so when we compute this, the first thing we're going to do is we're going to find the derivatives of each of the coefficients of I, j, and k. Right? And so f prime of t is going to be negative 1, g prime of t is going to be equal to 4, and then h prime at t is going to be equal to 3. We're just going to shove it into the formula, so it's going to be the integral from 0 to 1 of the square root of each of those derivatives squared with respect to t. All right, and clearly this is about as easy as it gets. Right? That's going to end up being 26 under the radical. The antiderivative of a constant is just the variable t in this case with respect to t. That's going to range from 0 to 1. And remember, our fundamental theorem of calculus says we plug in the upper bound, plug in the lower bound, and subtract. So that's going to be root 26 times 1 minus root 26 times 0, which is just our root 26. All right, so that's nice and easy. All right, not every function is as easy. All right, so let's take a look at a secondary example. Now this one we're going to have some other stuff going on besides linear coefficients. So we have I, we have t squared, j, and then we also have that t cubed for k. All right, and unfortunately that's going to be one that we don't necessarily like to work with. All right, so let's go ahead just like we did before, and let's find the derivatives. So f prime of t is 0, so we like that, nothing to contribute. G prime of t is 2t, h prime of t is 3t squared. We're going to shove all of those back into our integral. So to find the arc length s, that's the integral from 0 to 2, because that's the given interval, of the square root of 0 square plus 2t quantity square plus 3t square quantity square dt. And then if we go ahead and compute, that just winds up being 4t squared plus 9t to the 4th dt. Alright, so now we're faced with this antiderivative. Alright, and unfortunately it's not a nice antiderivative. There are a number of ways to try to compute this that are painful. So for instance, you could use a trigonometric substitution, you could try integration by parts, but we can turn this into a u substitution fairly easily. Let me illustrate how. Let's just factor out a t squared from what's under the radical. So if we factor out a t squared, that leaves us with 4 plus 9t squared dt, Or if we were to take the square root of that t square, we would rewrite this as 0 to 2 of t root 4 plus 9t squared dt. Alright, and that's actually a really easy integral to evaluate now, because if we take the derivative of what's underneath the radical, we get a u substitution, because we can almost get t, which is on the outside. So let's define u to be equal to 4 plus 9t squared. The derivative is going to be 18t dt, and that's almost what we want, because we have t, we have dt, we just don't like that 18, so we're just going to rewrite this as du 18ths is going to be equal to t dt. All right. And so now we're going to rewrite the integral. So that's going to be the integral now, not from 0 to 2, but from a to b, because we've changed the bounds. We're changing coordinates into u. We're going to have the square root of u. Okay, so remember that u is equal to 4 plus 9t squared, and then t dt is going to be du 18ths. So the new integral is going to be u to the 1/2, because it's under the square root, and then du over 18. All right, and now it just becomes a really simplistic integral to evaluate. This is going to be equal to u to the 3/2 divided by 3/2. We still have that 1/18. Okay, so to be able to get that, we add 1, and then we divide by the new exponent. And that's from 0 to 2. Now, I'm going to restructure this so that way it's easy to compute. I'll probably need a little bit more room here. So I'm just going to go down here just to make it nice and easy. Right. So if I rewrite this, then I'm going to get, and it's still a to b, it's not 0 to 2, sorry. So we're going to rewrite this as 4 plus 9t squared to the 3/2. Okay, so that's back substituting for u. And then we have we divide by 3/2, so that becomes 2/3. And then we still have that 1/18. Right. Now I'm going to have to squeeze this in here. I apologize. We have 0 to 2 now as the bounds. So we go over here. If we take 2/3 times 1/18, that should work out to be 1 over 27. So we get 1 over 27. We're going to substitute 2 back in first. So that's going to be 4 plus 9 times 2 squared to the 3/2 minus 1 over 27. We're going to substitute 0 back in. 4 plus 9 times 0 squared to the 3/2. All right, and one possible answer that we could get, we have this 36 times 4. We get 144, I believe. If it's 4 plus 36, it's 40. Excuse me. So we get 1/27 times 40 to the 3/2 minus 1/27 of 4 to the 3/2. All right. And at this point, you could certainly leave it like that. At this point, trying to fix it might be putting lipstick on a pig. No matter what, it's still going to be a pig. Another way to write this, if you really wanted to, and this would probably be like your back of the book answer, the simplified answer. 40 to the 3/2 is really the same thing as 1/27 times 40 to the 1/2. And then we have the 1/27. 4 to the 3/2 is going to be 8. That's a perfect value. All right? And so if we really wanted to clean this up and make it look, I don't know, lipstick on a pig, this would be 40 roots of 40 minus 8 over 27. All right, that would probably be the answer in the back of a textbook, etc. Okay, so hopefully that makes sense as to how to evaluate that. One last example of arc length is, although it looks messy, it's actually going to turn into something that's really nice. So we have this R of t, a cos t, a sine t, bt, ijk from 0 to 2 pi. All right, so as a reminder, this is actually going to be what our helix looks like. All right, and then a and b are just real numbers. All right, so when we compute this, we're not going to get an exact number for this, but we are going to get a formula to be able to find the arc length of this helix with a and b as the real numbers. All right, so let's start by finding f prime of t, and that's going to be negative a sine t. Let's find g prime of t, which is going to be a cos t. And then finally, h prime of t is just going to be b. And we're going to throw all of that into our formula. All right, so we have our integral from 0 to 2 pi, square root of minus a sine t squared plus a cos t squared plus b squared dt. All right, writings on the wall. This is just going to simplify really nicely because we get an a square sine square, a square cos square. And that just turns into a square. All right, so now it becomes really nice. So this is going to be 0 to 2 pi, just by doing the trigonometry, of a square plus b square dt. Now notice that there's no t's anywhere except for dt inside the integral. So root a square plus b square is a constant, and the antiderivative of a constant with respect to d is constant times t. So this is going to be equal to square root of a square plus b square t from 0 to 2 pi. We can substitute 2 pi and 0 back in there. So we get square root of a square plus b square, 2 pi minus 0, just by using our fundamental theorem of calculus. And so the arc length is going to be, for our helix, 2 pi square root a square plus b square. And I'll urge you to go onto the GeoGebra website and maybe just play around with different values of a and b to see what the helix would look like, and then you could try to approximate or even get an exact value as to what the arc length would be of that helix from 0 to 2 pi. Right? So hopefully this gives you a good overview as to how to compute arc length. The last thing we're going to take a look at is the idea of curvature.